Okay, so for today we're going to talk about the chi-square goodness of fit test for a binomial distribution. We're going to use this test if we have a set of data that we need to test whether it fits a binomial distribution or not. And we're going to use this example. So we have the data below showing the number of children born to 150 Greek women in a 5-year period in the 18th century. We want to test at a 5% level of significance whether the data is binomial with parameters n equals 5 and p is equal to 0.5. So the data here means there were 4 women out of 150 who had no children. There were 52 women out of the 150 surveyed who had 3 children, and so on. To proceed with this test, we have to identify the discrete random variable that we are considering. So we're going to say, for example, that the discrete random variable is x, and we are going to say that this x represents the number of children born to these women in that period. So to start with our chi-square goodness of fit test, we have to identify what is the null hypothesis and the alternative hypothesis. So the null hypothesis will always be neutral. So we're going to say this x is indeed following a binomial distribution with parameters 5 and 0.5. But the alternative hypothesis is the negation of that. So we're going to say x does not follow this binomial distribution. The data that we have does not follow the binomial distribution for n equals 5 and probability of success equal to 0.5. Okay? So the second step is to identify our significance level. This level of significance given at 5%, we have to convert that to a decimal value. The third step is finding the expected frequencies. So the expected frequencies will be the ones that will be compared to the observed frequencies in our data set. The second column actually represents our observed frequencies. To get the expected frequencies, we need to find the expected probabilities from the binomial distribution and then multiply that by 150. So let us just prepare our table, our list to contain the observed frequencies. I'll copy this. Okay. 4, 19, 41, 52, 26, 8. And let's look at let's input the number of children here. For us to get the expected frequencies, we need to use the frequency given by, the probability given by the binomial distribution function. So for example, for 0 number of children, the probability is going to be from our binomial distribution. I'm going to create a third column to correspond to these probabilities. So the probability that the number of children is equal to one of these, 0 all the way to 5. And we are going to use the distribution function option A, binomial PDF. So it will have 5 trials, 0.5 as probability of success, and x value equals 0. So that probability is going to be 0.03125. To get the probability that x is equal to 1, I do this, 0.15625, and I could do that all the way up to 5, but there's a faster way to do it in your list, I'm just going to L3 on top, and this is where I write my binom PDF with those trials and probability of success, but my x value, I'm going to say this is in L2. I have put my x values from 0 to 5 in L2, so I just paste that and enter. So my x values are from 0 to 5. L3 gives me the respective probabilities from the binomial probability distribution function. So this 0.03125 corresponds to that. The second one is 0.15625. Okay, I'll just copy the rest. 3125, 3125, 1563, 0.0313, or probably 125. Yeah. This one also is 1625. So to get the expected frequency, I'll create a new column for the expected frequency that will have to be taken from the probability that x is 0 multiplied by the number of women, which is 150. So the first row will be 4.6875. The second row will be 23.4375. But in my lists, this is just multiplying all numbers in L3 by 150. So I'm going to go to L4 and say every number in L3 I want to multiply by 150 so that it will immediately give me all those values automatically. So I copy that, 46.875, 23.6438, 4375, 4.6875. So now I have an expected frequency compared to the observed frequency. So in HL, you are meant to notice that there are expected frequencies that are less than 5. And this is a requirement that you are supposed to combine the columns or the rows next to it so that this expected frequency becomes more than 5. For SL, you will be guided more to do this, but for HL, it is an expectation that you will do this without being prompted. So we're going to combine the rows, the numbers beside it. Okay, so we're going to add 23.4375 into 4.6875. So I'm going to just add that and create another column, L5 in my calculator. 4.6875 plus 23.4375. Okay, and then I'm going to copy the others. And then 28.125. So now I have 4 rows. That means if I adjust, let me just copy that here for my new expected table, 28.125. 28.125. So this is my new expected frequency table. I should have a new observed frequency table. So I should also combine the rows corresponding to the rows that I combined in the expected frequency table. So this is going to be 23. as 34. So I have to rewrite that as well in my GDC. 52, 34, 23, 41, 52, 34. So perhaps it's good for you to take note where you put the observed frequency. I put that in L3 and I put the expected frequency in L5. So now we are ready to execute our goodness of fit test in this calculator. But first, we need to identify our degrees of freedom. So the degrees of freedom is normally equal to your n minus 1. Our n here is the number of rows that we have. So initially we had 6 rows, but we condensed that into just 4 rows. So I will have 4 minus 1, which is 3. For SL applications, there is always n minus 1, but for HL applications, there is an added number that you need to subtract in that degrees of freedom, and that's going to be the number of parameters that have been estimated before you execute this. The parameters here are n and p. If one of these, one or both of these are estimated, we subtract that from the degree of freedom. So but this time it's given, so we use the degree of freedom to be 3. So part 4, we're going to go ahead and compute for our chi-square calculated value. So I'm going to press stat, tests, and then press the up arrow. Chi-square goodness of fit test is option D, and then I'm going to put my observed values into L6, and my expected values is actually in L5 with the degree of freedom that we found here. Okay, so again, it's a good thing to note which list, what is the name of the list that you used for the expected and the observed, and the degree of freedom is found here, so that is 3. Okay, so the chi-square goodness of fit test gives 2 values. Chi-square calc is 3.46 to 3 significant figures, and p is equal to 0.326. And then now we are ready to make our conclusion based on the values that we found. We can use the chi-square calculated value to compare it with a critical value if the critical value is given. So if the chi-square calculated value is greater than critical value, then we reject the null hypothesis. But if it is not given, we just use p. So essentially, you could always just use p to conclude whether or not the chi-square critical value is provided in the question. So our p is 0.326, and we are going to compare that with the alpha level, significance level of 0.05, and we are going to say that it is actually greater than 0.05. So if p is greater than the alpha level, we're going to accept the null hypothesis. So after accepting the null hypothesis, we state our conclusion. So we're going to say that x, this data actually comes from a binomial distribution with n equals 5 and probability of success equal to 0.5.